All right, this is number 4, and this is a bit more work than the others. And it makes sense. It's a more complicated problem. What if we have more coming into a tank than leaving? That's going to mean that volume is not constant. It still starts at 100 gallons. We still have 35 grams of salt to start with. We have concentration going in. So fortunately, setting up the differential equation isn't any harder, really. It's a little bit. It's still the basic premise. We have something coming in. We have something going out. And we have the same stuff coming in as the previous couple situations. We have 0.5 grams per gallon, and we have 3 gallons per minute. Right? So that's going to give us 1.5. Over here, we have whatever amount of salt in the tank divided by the volume, but the volume is not constant. So we'll have to address that. And we have a different flow rate, 2 gallons per minute. So this volume, what can we say about it? Well, I mean, intuitively, we have more coming in than going out. The volume should start at 100 and become more, right? How fast? Well, if we gain 3, lose 2, then we're gaining a net of 1 gallon per minute. So it's 100 plus T, 1T. A fancier way of looking at this is V naught plus the flow rate, I should say the net flow rate, times time. Right? Flow rate is going to be gallons per minute times minutes, gives you gallons to add on to the initial amount. So here we have 100 plus T. So then our differential equation is dm dt equals 1.5 minus 2m over 100 plus T. And let's rewrite this a little bit. So it's dm dt plus 2 over 100 plus T m equals 1.5, and we have the same initial condition. So this would be A. This is setting up the initial value problem. So B is solving it. So to solve it, step 1, solve the homogeneous differential equation, which is dm dt plus 2 over 100 plus T m equals 0. So this is a separation of variables. So separate, we'll have dm over m equals a minus 2 over 100 plus T dt. Integrate. And I go back down here, we'll have an ln of absolute value of m equals a minus 2 ln of absolute value of 100 plus T plus a constant. Now, we can exponentiate both sides here. Let's just do it. So we'll have a absolute value of m. Move the camera a little bit. Equals an e to the minus 2 ln absolute value of 100 plus T, e to the c. Now this stuff can't come down until we bring that minus 2 inside, right? So this has to come as an exponent. So this is going to be e to the ln of 1 over 100 plus T squared, e to the c. And that simplifies down quite nicely. So absolute value of m is e to the c. And we can take off the absolute values here. We're going to take care of them over here anyway. So any pluses and minuses will be dealt with. And this is always positive anyway. So that means that m, take out the absolute values, we get a plus or minus c. So it's going to be a constant over 100 plus T squared. So this is the general solution to the homogeneous. Okay, on to the inhomogeneous. So the idea is then to say, well, maybe this is an unknown function. All right. And plug into the inhomogeneous. We tear this off. So then we're going to have the dm dt term is going to be an a prime over that 100 t squared, and then a minus 2a prime over 100 plus t cubed. And then, where's the rest? Then is a plus 2 over 100 plus t, a over 100 plus t squared equals 1.5. These terms cancel out. So we have a prime over 100 plus t squared equals 1.5. So a prime is 1.5 times 100 plus t squared. So then a is 1.5 divided by 3, 100 plus t cubed plus c. 1.5 is 3 halves. So this is just 0.5, 100 plus t cubed plus c. This is a. This is our function a. Our supposition is that our solution to the inhomogeneous equation is a function a that we just found divided by this stuff. So let's do that. So m of t, let's take this stuff that we just obtained and divide it by this stuff. Notice there are no exponentials this time. That's curious, right? And we can clean this up a little bit. This is 0.5, 100 plus t plus c over 100 plus t squared. This is going to be nice for limits later, actually. Okay, let's use our initial condition. Initially, we have 35 grams. So that's going to be c 0.5 times 100 plus c over 100 squared. So that's 50 plus c over 10,000, which equals 35. This is the equation we want to solve. All right, so what do we got? We got 35 minus 50 is negative 15 times a bunch of zeros. Big number. All right. So C is minus 15, 150,000, sorry, minus. So then our solution, m of t, is 0. Well, let's write it like this. Let's write it like 50 plus 1/2 t minus a big old number over this stuff. Right? Now that looks weird. Now, what does this look like as t goes to infinity? This blows up. So the limit as t goes to infinity of m of t is infinity. Right? This term here would eventually go to 0, and this would not. Also, FYI, this is our particular solution to the inhomogeneous equation. So, what gives? Why is that the case? Well, let's think about it. We have more water coming in than is coming out. And, oops. So let's see, we're bringing in 1.5 grams of salt at a given time. Before, in the previous problem, 50 was okay, right? We had reached 50 was at our equilibrium. Well, at 50, we were losing 1.5 grams, right? That won't happen this time. At 50, what would be happening? Well, we're also gaining a gallon a minute. So it's a little hard to kind of conceptualize this. So what kind of things could we do to understand this? One, and this is kind of interesting, I haven't fully thought about it yet, but you might remember at some point studying slant asymptotes. Right? So a slant asymptote is what this thing's going to become eventually. Eventually, all the solutions will get glued to this line. I'll do a video with some screenshots. So we're going to end up, the system is going to act as if we had started with 50 and we're adding a half a gram per minute. So that's an interesting clue. Eventually, the system will act like it had started with 50 grams and a half gram per minute were added. Maybe there's a clue there for understanding this. Suppose we had started at 50 grams here. At 50 grams, we would be losing 1 gram per minute, but gaining 1.5 gram per minute. We would also be gaining 1 gallon per minute. So that's a little tricky there. But then again, we're not looking at concentration, we're looking at total mass here. So that's probably the way to think about it. Yeah. So if it were 50 grams, then we'd be gaining 1.5 grams per minute while losing 1 gram per minute for a net gain of a half a gram per minute, which is the slope of this slant asymptote. And so one imagines then that what happens, because we didn't start with 50, is that what happens is that the system builds up to 50 or kind of works towards the solution. Heck, I'm going to pause here and I'll do some screenshots and we'll talk about the solution a bit more. Okay?